All right, welcome back. We left off on page 59, and we had discovered that for functions that had really nice properties, in other words, that they had an antiderivative, then the integral over a closed smooth loop, meaning that it went back on itself like that this would be 0. And if we did an integral on something like this of a function, then we would just get the antiderivative, and then we'd have the final point minus the beginning point. And that's where t equals a started here and t equals b ended there. So it's basically the fundamental theorem of calculus for a complex plane. The next thing we wanted to do is we wanted to talk about the abstract definition of an antiderivative by integration. And so we're doing the same thing that happened in calculus. We are linking integrals were areas, integrals were antiderivatives, and they came together. So we need a definition of a functional antiderivative, and then we want to see if they come together. So here is a very neat definition. So the definition that we're going to make for a new function, f of z, and we're going to prove that it's actually the antiderivative, but right now capital F is just going to be a definition of a function. So we need to start with the function f, and this function f has to be a very nice function. It has to have the integral over a closed curve equals 0 for all curves inside of a place gamma where f is continuous in gamma. And now this region, sorry, not gamma, G. This region G, you need to think of it, those in topology, as an open set. Those that we've just seen it now, it has space inside of it. We can put disks so that when we talk about any point, there's room around the disk. All right, so we're going to define this f of z in the following way. First, z is an element inside of G, so it's a choice element. And we're going to have a fixed z naught in G as well. So here is z naught, and here is a point z. And we're going to let gamma 1 be such that gamma 1 of A starts at z naught, and gamma 1 of B ends at z, and gamma lives entirely inside of G. So basically this is a path that wanders like that. And now we're going to define f of z as that path integral of our function, starting at z naught and ending at z. Now, this seems like a fairly simplistic definition. So let's look at some immediate consequences of it. So first off, here's this thing G. Here's z naught. Here's z. And here's any old gamma. So why don't we take another gamma? So we'll call this gamma 1 and gamma 2. And let's observe that the integral of f over gamma 1 minus gamma 2, which means go this way and then go backwards there, that's going to be 0, which implies that the integral over gamma 1 of f will be the same as the integral over gamma 2 of f. So it doesn't matter which path that you go from z naught to z, this is your defined value of f of z. So you may pick any gamma that's inside of G to do this. So the function is well defined. That's important. It doesn't matter which path you take. You must stay within inside of G. All right, now that we've done that, let's then ask ourselves, what properties does this function f have? Well, I'm going to show that it's differentiable. Now, the definition of differentiable isn't all that crazy. It's simply you're going to take a limit of the difference quotient. So let's do that. Let's write down the limit of the difference quotient. So we want to take f of z plus a small number minus f of z. We want to divide by h, and we want to calculate that. So I need to go over here, and I need to imagine that here's your z, and you moved over some z plus h. And let's make it a straight line. Let's call that gamma 3. Straight line from z to z plus h. So what is f of z plus h? It's go along gamma 1, any gamma, we'll pick gamma 1, over to there. And what's f of z? Going along gamma 1 to there. So we're going to throw away gamma of 2. That was just to show that didn't matter which gamma we used. And so this statement right here says, go along gamma 1 to z, integrate, get the value. Go along z to z plus h, integrate, get the value. Take the difference, divide by h. Well, that difference in the top looks like somehow it's going to be just the integral from here to here. So we need to talk about how to calculate this. All right? So I'm going to put z here. I'm going to put z plus h here. That's a straight line. We'll call that gamma 2. And here's z naught, and there's some gamma in here. Now, we're going to be taking a limit as h goes to 0. And as h is, we don't know how people are taking that limit. So remember, here's our g, which is that topological idea of an open set. And the first thing I want you to notice is under this limit, I'm going to make sure that h is small enough so that I'm in that ball around z, that I'm inside of g. And this can be done because we say that we have that topological definition of G being an open set. That's what we're working with. So it's going to be small enough so that we're not outside of G. So I should adjust it this way. This picture has been reduced far enough so that we're inside of G. All right, so now we're going to do some calculation. So first off, f of z plus h is the integral along gamma 1 plus that line of f, and minus, and now it's the integral along the gamma 1 of f, and that says it's just the integral of f along the line. All right, so that's not a big calculation, so this is useful. All right, now I'm going to calculate, that's f of g plus h, and that's f of z, so I've taken their difference. Now I'm going to divide by h. I just called that L, sorry. So I'm going to divide this by h, but I'm not going to do the limit of that. I'm going to do another trick. I'm going to do the following. I'm going to do f of z plus h minus f of z over h minus f of z. Now that is what I want this limit to equal, because I want that capital F to be an antiderivative. So if I take the limit of this and get 0, and since that's constant, z doesn't move, I'll just prove that that limit equals that. So now I'm going to subtract off from this f of z. Now, that looks really kind of odd, doesn't it? This expression. All right, so let me continue with that. I have f of z plus h minus f of z over h minus f of z being equal to the integral of the f over that line segment L on h minus the constant part f of z. Well, what is the integral over the function 1 on the line segment L? Why, that is just the length of L, the straight line right there, right? But here was z, and here was z plus h. We know that distance. That's the distance h. And so this is not terribly bad to use. If I get a common denominator here and put an h and an h here, I can now say that I did this integral to get that h. So I'm going to replace that with an integral and write the integral over f over the line segment L minus the integral with f of z in front over L of 1 all over h. Now, we're going to combine these. Doesn't matter that these are two different expressions. What matters is that's constant. This is an integral over a path, integral over a path. They share whatever dummy variable I like. So this is f minus that fixed f of z integrated over L over h. So this is an integral of a varying function on a line segment minus a constant. Now, we're going to use the ML theorem. We know that this is less than or equal to the max of the function f minus f of z. Realize z is fixed. F is varying over the path L times the length of that path, which is h, which is over h. That cancels. So we've just shown that this is less than the max of the function f minus f of z, and this is the max on L. Ooh, we've made good headway. So we have z, we have the straight line L, we have z plus h, and now we want to know the max of a function minus a constant over this value L. But now we're going to go all the way back where we said one thing special about our function before we began. We said that we're going to do this, but we required, whoops, didn't go back far enough. We required f to be continuous in G. So what's it mean for a function to be continuous in a domain? Well, here's G, it's continuous. It means that given an epsilon, there exists a neighborhood around z where the function minus other values are bounded by epsilon. So guess what? Under my limit process, I know there exists a length delta that's bounded around here, get h small enough that this will be less than epsilon for any epsilon. So we've just proved that f of z plus h minus f of z over h minus this little f of z is less than epsilon, which implies that under the limit as h goes to 0, we get f of z. And we have just discovered that the integral from z naught inside of any domain where a function f is continuous, where we can have closed-looped integrals of that function f, then any integral on a path to z, this integral is the antiderivative of the little function f inside of here. Ooh, that's so powerful. Now, we don't need perfectly smooth paths. Remember, we can do this. We can go to corner, corner, corner. We can go like that as well. That's a piecewise connected smooth. It's okay if we keep a finite number of paths that give us trouble. Well, that's pretty powerful. It says that continuous functions in a domain that have closed loop integrals are sufficient to say that the function has an antiderivative. And the antiderivative is actually done by doing a path integral. That's pretty cool. So now, in section 4.3, we have to introduce a new idea because it's important. it's going to show that some paths are far easier than other paths. So I'm going to introduce an idea that's very simple. It's not hard to think of. It's super grungy to implement, and got a good picture for you, I think. So let's start with a domain inside of the complex numbers, open set, and let's have 1 and 2 different parameterizations. Now, I'm going to equalize them. If that was an A to B, C to D, it doesn't matter. I'm going to reparameterize them. We know that's perfectly fine. We're going to parameterize them from 0 to 1, both of them. So now, what's interesting here is there's 2 things that we could require. We could require them to start at a point and end at the same point. That's fine. Or we could say here's gamma 1 and here's gamma 2, different points. I think this is the most general one, and I'm going to work with that one. Now, what I'm going to do is produce the average of these 2 smooth continuous functions. And what's weird is that average actually moves the one function to the other. It bends it in a nice pattern. And all that's required is a 2-variable function to change one function into the other. Now the standard one, and I'm going to call this the standard one, it's by no means the only one. If I could find Joe Bernstein's presentation, I can show you a radial construction. I am just going to do the planar average, the standard construction. So I'm going to define a function h of t comma s. Now, what's weird about it is that they put the s after the t, which I absolutely hate, but somehow that it's important. In the long run, apparently it's historical. It is going to be an average of these 2 things. I'm going to take 1 minus s gamma 1 plus s of gamma of 2. Now, this are the things that have the t in here. Now, notice that when you start at 0, you just get the function gamma of 1. So this path right here is actually h of t0, this path. And I want you to notice that ht of 1, well, 1 minus 1 is 0. This is gone. You're now at gamma 2 of t. And so here is ht of 1. So this function is a surface in 2 variables, and one slice at s equals 0 is 1, one slice at s equals 1 is different. What about all the ones in between? Well, this is a continuous function, this is a continuous, this is continuous, this is continuous, this is a continuous function. All of these intermittent ones in between move one from one to another. This is called a homotopy. It is a smooth moving. Now, you guys have taken a piece of Play-Doh and pushed on it, and hence here's an orange, and if I squeeze it, I haven't broke it, but I'm changing the shape. I'm doing homotopies on this. I'm messing with it and making it different, but the same. I'm continuing. There's no cracks, no breaks. So I'm going to demonstrate one of these. Hopefully it'll pop up in the computer really well. However, if it doesn't, we'll take care of it. So put that there. I think you can see it. I have put on Desmos one function, which is the circle, the first quarter of the circle. I took the square root of 4 minus x squared. I think I'm going to drop the light. That might help. Yeah, I think that helps. So I got y equals the square root of 4 minus x on 0 to 2. That's that circle. And I got x cubed over 2 minus 2x plus 4 on 0 to 2. So it's up there. And now I put in the averaging homotopy. And so the standard one. And so I'm now going to show you that it slowly every s between there is a nice smooth function, and by the time we reach 1, it becomes the other function. Homotopies smoothly change one object into another. This is a homotopy. Now you can also do homotopies between fixed endpoints. You can have one endpoint, the other endpoint fixed. So here's a fun one in the book. I think you should try the book one and see if it works. Do it on Desmos. It's a little complicated. Do one piece of it. That's sufficient. They wrote down the following crazy homotopy. Now, the reason I'm going to write this homotopy out is because when you first look at it, they have a piecewise listed function over here. And so they're doing the standard homotopy. They're doing the standard homotopy on averaging, 2 pi I t. That's a circle. This is going to, as t varies from 0 to 1, that's going to go around a circle. So it looks like you have a circle, radius 1 in front. So you have a circle that from 0 to 1 goes around one time. That's this. And you're averaging it with, well, 3 plus 24 ti, but it only varies from 0 to 8, which means that when it gets in there, it goes from 3 to 3t. Oh, so this piece, when you plug in 0, starts at 3. By the time you get to 1/8, you get to up to 3i. I think that's Bjorn's gamma. Boom. And so over the t of 1/8, which is 1/8 of this circle, this is going to average this function to this function, and as you start at, and which value of s, when s is 1, we're here. When s is 0, we're there. Yeah, it's going to move this out. It's going to smoothly make that circle into a straight line. And the next section is going to do it here, and the next section is here, and here, and here, and here, and here. These homotopies are smoothly making a circle into a square. This is a cool one to do. I think you guys, if you want to have some fun on Desmos, you can put this all together and make a slider, and boom, you can make a circle into a square in a nice little movie. Want some extra credit? Do it. This is the one that Joe Bernstein did for me years back, and I would love to see this one done. So this is what we talk about in mathematics when we say objects are smoothly homotopic to each other. Now, why have we done this? That's interesting. The reason it's interesting is we're going to do some differential equations, some partial differential equations, and we're going to prove something very powerful. And this is going to be Cauchy's theorem. And what's so fundamental about this theorem is it's going to allow us to evaluate massive function values in the complex plane that are crazy, and integrals that you can't imagine having done before. And on top of that, we're going to be able to do integrals in the real plane because we developed this tool. Now, it's pretty obvious when you develop a tool like a hatchet that it's going to hurt something, it's going to chip at it. But it's not quite so obvious until you start using one that the longer the arm of the hatchet, so you make it an axe, that you can deliver more power because of something called rotational motion and torque. Now, if it gets too big, you can't even swing it, and there's trouble there. This is a tool where it's got a lot of power. This is a killer tool. All right, I've reached page 63. I'm going to cut this off because I had trouble with the upload, and I will email problems specifically associated with this. But this one, if you want to do that one, that's extra credit.